Okay, I'll get started. Just wanted to begin with an announcement about Test 1 and the schedule for Test 1. So Test 1 is being graded now. We hope that we'll have the scores posted by Friday of this week, so you'll see those in Canvas. I plan to have the solutions posted after makeups, which will be on Friday of this week. You'll get your exams returned in the Monday recitation at the beginning of next week, and then you'll have 1 week for any questions about regrading to the following recitation the following week. So that's the planned schedule. Any questions on all that? If any questions come up or you think about anything, you can just email me or you can just ask me. So if not, I'll move along. Today's class, we're moving along from electricity, which was the content of Test 1, to magnetism and electromagnetism, which is the content for Test 2. In today's class, I wanted to work through an introduction, a first introduction to magnetism. I want to work through these 4 bullets on magnetism. So I'm going to talk a little bit about magnetic attraction and repulsion. I'm going to talk about magnetic north poles and south poles. I'm then going to talk a little bit about the magnetic field that carries, conveys, mediates the magnetic force, like electric fields carry, convey, mediate magnetic forces. And towards the end, I'm going to be talking about the field equation. We had previously met an electric field equation that precisely said how electric forces work through electric fields. We're going to meet today, the only equation we'll meet today is the magnetic field equation that says precisely how magnetic fields carry, convey magnetic forces. And so this is the plan for today. It's basically resembles what we did in electricity. There we talked about electrical attraction, repulsion. We started with that. There we talked about electrical charges, positive and negative charges. There we talked about the fact that the forces were carried through space by a real material field, the electrical field, and we wrote down a field equation for that real material electrical field. So exactly the same path, really. Exactly the same plan. This is just an introduction to get us going. I wanted to remind us about the beginnings of electricity and the beginnings of magnetism, because the beginnings of electricity and magnetism occurred in ancient times, at similar times. They occurred from similar observations, similar but different observations. So electricity was first documented as this attraction of, I don't know, wool or fur or straw or hair by amber when it was rubbed. And that was the first documentation of electricity. The first documentation of magnetism was that there were certain magnetic materials, certain magnetic rocks, iron ores, that would attract one another. And that was the first documentation of magnetism. Nowadays, we know, that's the second bullet here, that in the electrical case, the amber attracting the hair, that was actually a manifestation of electrical force between the electrically charged building blocks of matter. So it's really a clue to matter's nature and assembly out of charged building blocks. Nowadays we know that the attraction between certain magnetic rocks is actually also a manifestation of a magnetic force between charges, the charged building blocks of matter. So actually, electricity is ultimately arising because all material is built out of charged building blocks, and electrical forces arise because of that. Magnetism, the same thing. Magnetism arises because matter is made out of charged building blocks, and that leads to magnetic forces as well. So electrical forces and magnetic fields actually have the same roots. They have exactly the same roots. Their roots are both electrical charge. Electrical charge produces both electric and magnetic forces. So that's a very important point. You might wonder if magnetism is important, or is it not so important? I think it is very important. Magnetism is very important to us. Let's walk through these pictures. The most famous magnet for us is the Earth is a magnet. The Earth is a magnet, and that magnet produces magnetic forces, magnetic fields. The Earth is surrounded by magnetic fields that create magnetic forces. Those magnetic forces created by the Earth's magnetic fields actually shield us. They shield us from deadly radiation from the sun and the galaxy and the universe. So there's deadly radiation from the sun, from the galaxy as a whole that we live in, the Milky Way, from the universe, that would kill us off if it wasn't for the fact that around Earth is this magnetic umbrella, this magnetic shield that's preventing the radiation getting down to sea level, getting down to us and all the animals and life on Earth. So we're saved by magnetism. That's one reason it's important. Magnetism has expanded our worlds. This is an ancient expansion of our worlds. The compass, the invention of the compass, that allowed people to navigate across the Earth, across the oceans, and explore the Earth and the oceans. And that opened up a whole new world for humankind, that exploration. That was made possible because of the inventions of the compass, a magnetic device, and the fact that the Earth is a magnet, has a magnetic field. So that was important. Actually, we think we're smart. We invented the compass, and we were able to navigate over the Earth. Birds had already done it. Fish had already done it. They have inbuilt compasses that allow them to navigate, migrate, by detecting, like a compass, the Earth's magnetic field. And so they have sensors that detect the Earth's magnetic field. So birds and fish were already doing this. Magnetic fields and forces and magnetism have also expanded our world, not to that world of exploration, to the very large, but to the world of the much smaller. We see inside our brains, inside our minds, how they work, how they operate through magnetic resonance imaging. That's a magnetic technique that allows us to look inside our brains and see the operation of our brains. So we're expanding our world in that way with magnetism. And then finally, I said over here that magnetism saved our lives because the Earth is a magnet. This is another sense in which magnetism is saving our lives. It's literally documenting all of our lives, right? Every time I use my credit card, no matter what I'm buying, it's recorded magnetically somewhere as little bits of information. Take a photograph, use your phone, it's all being recorded and digitally stored. And so there's a huge amount of data that's now stored magnetically. That is really a record of all our lives, for good or bad, right? And so that's another important use of magnetism. Okay, there's even a huge scientific significance of magnetism. I've talked about sort of life-saving, life-changing significances of magnetism, but there's a huge scientific importance of magnetism. During Physics 211 and Physics 213, during the stories of 211 and 213, you actually meet two of the greatest scientific events that occurred, physics events that occurred, and they're two of the great unifications that occurred in physics, the two joinings in physics. The first one was due to Newton, and you meet it in Physics 211. It's the joining together, the unification, the combined understanding of terrestrial motion, so like you walking around or riding a bike, and celestial motion, the motion of the moon and the planets and the sun and so forth. Until Newton, those were two just separate things, unexplained. But they got joined together. This is first great unification in physics. So that's an immense, if you're a physicist, that's like a fantastic story. You dream about it. The second great unification in physics, came later, a bit later, and it was the joining together of electricity that we've just been talking about with magnetism that we're about to talk about now. So that's the second great unification in physics, second great story in physics, and that is what we're going to explore over the next lectures up to test 2. So huge magnetism is a huge importance in physics. Okay. Well, enough of that. Let's actually get on with some content. Let's talk about attraction, repulsion, north poles, south poles, and magnetic fields conveying magnetic forces. I want to move on to that. Let's start with poles. As I'm sure you know from kindergarten, just like for electricity, we found that we have electrical attraction and repulsion that are due to positive and negative electrical charges, where like charges will repel one another and unlike charges will attract one another. We have magnetic attraction and repulsion that arise due to magnetic north poles and south poles, we name them, and like poles repel one another. Two north poles will repel, two south poles will repel, and unlike poles will attract one another. So a north pole and a south pole will attract one another. So there's a big parallel there, right, between positive and negative charges and attraction and repulsion. In electricity, north and south poles, and attraction and repulsion in magnetism. And so I just wanted to introduce that. And I think I want to show you a picture of it. This slide just summarizes it all. Here's two magnets upstairs here in this top row. Magnets, like fridge magnets or any magnet, the magnets on this desk here, they have a north end and a south end, a north pole and a south end. And if you have two magnets, they're like ends, their like poles will repel one another, and their unlike poles will attract one another. So in this configuration here, the two south poles are neighboring one another, nearby one another. This is a repulsive case. This is going to be repulsion. In this case here, we've got two north poles that are neighbors to one another, nearby one another. So these two poles will repel one another. And then finally, here's the other case, when you've got a north pole and a south pole, or a south pole and a north pole. In that case, you get attraction. So these two magnets are pulled together. So that's shown here. And so this is a summary, just like two positive charges will repel, two negative charges repel, positive and negative charge attract one another. This is a summary of that. Just want to show you a video of that. I mean, just in case you don't believe it, we made a video of it, wherever it is. So what you're seeing here is a magnet that can be rotated on a little turntable. And then you're seeing a friend of mine who's bringing up another magnet and creating attractive and repulsive forces. Now, the magnet on the turntable has a red end marked the North Pole, a South Pole marked in white, and the person bringing up the magnet also has another identical magnet with a North Pole and a South Pole in red and white. And when you bring up a like pole, you're going to get repulsion, and when you bring up a unlike pole, like there, you're going to get attraction. Now, if you look at this, these attractions and repulsions are actually much larger than the attractions and repulsions that we got with rubbing the cat's fur on the glass rod, rubbing the silk on the plastic rod. So this attraction repulsion of magnets is very easy to see. This attraction and repulsion, original attraction and repulsion of magnetic ores, iron ores, is very easy to see in the special cases of materials that are magnetic. In electricity, we said that you could pretty much rub anything with anything. You know, glass with cat's fur or silk, plastic with cat's fur and silk, or anything with anything, and you could create electrical attractions and repulsions. Not true in magnetism. We have to have very special materials, magnets, to expose, to see electrical attraction, repulsion. But when we have those special materials, the magnets in the video, then the electrical magnetic attraction repulsion is very large. Okay. I want to talk about magnetic fields, because magnetic fields mediate magnetic forces, like electric fields mediate electrical forces. So we're going to talk a little bit about that. I'm going to show you a few pictures of magnetic fields. I'm going to demonstrate some magnetic fields, and then we'll get on to the you'll be pleased to know the field equation. On this slide here, I'm picturing a well-known electrical field that's upstairs, and I'm picturing a well-known magnetic field that's downstairs. So the field is pictured, the electric field's pictured as field lines, these orange field lines, and we discussed that before. The magnetic field is pictured also as field lines, but this is a new field. We haven't discussed this before. The familiar field upstairs, electric field, is the field of what we call an electrical dipole. That's just the name we give to an arrangement of one positive and one negative charge of equal sizes but opposite signs. So this is an electrical dipole field. We've talked about this. And downstairs here, this is the magnetic field, kind of a corresponding object. It's the magnetic field of a magnet, but it's a magnetic field that's created by a north and south pole, kind of like a positive and negative charge. And so this is called a magnetic dipole. And it's just the name we give to a north and a south pole. Yeah?
Would it be wrong to interchange N and S and positive and negative? Like, would it be wrong to call north positive and south positive?
That's a great question. Okay? So, and it's exactly like the question, is it, supposing you reverse the the naming of positive and negative charges. There would be absolutely no difference. If we all agreed, right, we're going to change the convention, right, like changing the side of the road you're going to drive on. If everybody changes the convention that a South Pole is now going to be a North Pole and the North Pole is going to be a South Pole, then there'll be no change. All the forces would be the same. All the magnetism will be the same. It's just a naming convention that we invented. You know, in the electrical case, just to get off track for a bit, the fact that electrons are negatively charged, that also was a convention. And that was a very unfortunate convention, because when we think about electrical currents, the electrical currents are defined to flow in the opposite direction of electrons that are carrying the current, and that's because the electrons were giving a negative charge. And who did that? Who do we blame for that mistake? We blame a US president. Benjamin Franklin is not a president, but a US politician. We blame Benjamin Franklin for that mistake, because he was first, before a politician, he was a scientist. And he came up with the idea of positive and negative charges. He was the one that named electrons to be negative charges. And since then, we've been stuck with this awkward convention about electrons, which are basic charge carriers in physics, that they have a negative charge and the currents flow in the opposite direction to which the electrons move. Okay. Let's take a look over here. We've got the field lines upstairs for the electric dipole, the field lines for the magnetic dipole. And if you look at these patterns, they look very similar. So if you look at the pattern at the top, the field lines are coming out of the positive and negative, out of the positive charges and into the negative charges. They sweep around from the positive charges to the negative charges. Where the field lines are densely packed, that's a strong field. Where they're loosely packed, that's a weak field. And the direction of the field lines tell us the direction of the field. Same thing down here. We see down here that the field lines are coming out of the North Pole. They sweep around to the South Pole. Where the field lines are densely packed, that's a strong magnetic field. Where they're loosely packed, that's a weak magnetic field. And the direction of the magnetic field lines down here tell us the direction of the magnetic field. So everything looks very similar for the electrical dipole and the two charges, and the magnetic dipole and the north and south poles. There is actually a somewhat subtle on the picture difference, though. The somewhat subtle difference on the picture is that the positive charge is a source of field lines. So they literally come out of the positive charge. The negative charge is what we call that sink of field lines. They literally drain into the negative charge. But that's not true for the North Pole and the South Pole. I tried to draw it here. These field lines, whilst they're coming out of the left-hand end of the magnet and going into the right-hand end of the magnet, they actually stream through the magnet. These field lines are just loops of field. So they don't actually have beginnings and ends. They just form loops. So that is a significant difference. Here's a sketch of this most important magnet. This is the sketch of the magnetic Earth. And I just wanted to make a few remarks about it. There's some interest coming to north and south poles. There's a convention here that is right now also unfortunate. So here's the Earth. The Earth spins about its axis, and upstairs here is what we call the North Pole, the geographic North Pole. That's where the Arctic is. And downstairs here, at the bottom here, is where we call the geographic south pole. That's where the Antarctic is. But these geographic poles are really defined by the fact that the Earth is rotating. The Earth is spinning. That defines a pair of geographic poles where the axis of spin passes through the Earth in the Antarctic, passes through the Earth in the Arctic, and we call those the poles, the geographic north and south poles. So that's geographic north and south poles. But also marked on here is magnetic poles. There's a magnetic pole upstairs here, and there's a magnetic pole downstairs here. And a couple of points about that. Firstly, the magnetic North Pole is located at the geographic South Pole. So Antarctic at the South Pole is magnetically a North Pole. Arctic at the North Pole is actually magnetically a geographic South Pole. So just like we got the sign wrong with the electrons running around the circuit, we've got the sign wrongs right now with the geographic and magnetic poles being oppositely orientated. So that's a little bit confusing. To be fair though, a couple of points to be fair. The Earth's magnetism is due to the fact the Earth has a dense iron core. Remember, iron ore was magnetic. This iron core is magnetic, and that creates the magnetism of the Earth. What's really interested in, over timescales of hundreds of thousands of years or millions of years, that magnetism of the Earth's core will actually reverse. So there's reversals of the Earth's core. There's been many reversals of the Earth's core. And right now we're just living in a time where the magnetic north is at the Antarctic and the magnetic south is at the Arctic. If we wait 100,000 years or a million years, then that might reverse. It might be the other way around, the opposite way around. So we're just accidentally living in a time when the geographic and magnetic north and south poles are opposite one another. But if we wait long enough, they'll be aligned with one another. And then if we waited even longer, there'll be another reversal and they'll be opposite one another. Also, one other point, the magnetic north poles and south poles don't align exactly. They're not exactly aligned. And you see that on this diagram here. There's the magnetic south pole is actually somewhere in Greenland, for example. I don't know where the magnetic north pole is, somewhere in the ocean, but they're not exactly aligned with the geographic poles. This is a sketch. No, it's not a sketch. It's a real photograph. Sorry. On the left-hand side, of a magnet, north pole's down here at the bottom, south pole's down here at the top, and the magnetic field around the magnet is being illuminated, basically, is being shown, displayed by iron filings. So iron filings are just tiny, tiny granules of iron, like little iron dust. And if you immerse them in a magnetic field, due to, for example, this magnet here with its north and south poles, they themselves get magnetized in that magnetic field, and that magnetization of the iron filings causes them to do two things. Firstly, they tend to move towards the regions of higher magnetic fields. That's one thing they'll do. Secondly, these filings will tend to line up with the direction of the field lines. So they literally respond by being magnetized to the magnetic field, and they literally actually illustrate what the magnetic field looks like. So you see the iron filings are closely packed upstairs near at the South Pole and closely packed downstairs here at the North Pole. That's because the iron filings move towards the regions of high magnetic field. So near the poles is high magnetic field. You also see that the iron filings seem to trace out these lines which are the lines of magnetic field. So they're literally showing you the direction, the orientation of the magnetic field. Magnetic field's coming out of the North Pole at the bottom, heading into the South Pole at the top, and it's looping round from the North Pole to the South Pole, and the filings are showing you that pattern. I can show you a little demonstration of that on the document camera. So I'll go to the document camera. I have some iron filings in castor oil in a box. And I have a little magnet. It's a little magnet, but you won't be able to read it. But on one end, the red end is a North Pole, and the other end is a South Pole. And this is a neat little box because it has a little cylindrical interior in which I can input the magnet. So I can drop the magnet in the box. And I'm going to put that on the document camera, and we're going to watch. When I put the magnet in the box, I'm going to shake up the box so the iron filings are just distributed everywhere. And then we're going to watch those iron filings as they move around and line up with the magnetic field of this magnet when I put it in the box. So I'm going to put this on the screen. Here we are. And I put the magnet. And this may take a moment or two. You just see the North Pole here, the South Pole here. You start to see the pattern of field lines emerging. And what you're seeing is there's tens of thousands of iron filings in that castor oil. And those individual iron filings are all getting magnetized. They're all they're all being bathed in the magnetic field of the magnet. And one thing, they want to move. They want to move to regions of stronger magnetic field. Other thing, they want to align themselves. They want to line up with the magnetic field. And so you see them all clustering around the North Pole over here on the left and the South Pole over here on the right of the magnet. And between the poles, you can see these sort of streams of iron filings stretching out from the North Pole to the South Pole. And so iron filings are just a great tool for actually literally imaging what the magnetic field looks like. If you had any doubt that the magnetic field is a real material thing, drop these iron filings in the region of a magnetic field and it'll show you the map of the magnetic field. We can't see it with our eyes, but we can see it with this tool. Okay. I wanted to show you a couple of other pictures of magnets and iron filings illuminating the magnetic field. So this picture here was a single magnet where we had one North Pole, one South Pole. But we also talked about pairs of magnets where like poles repel one another and unlike poles attract one another. And so I got two more pictures, this one here and this one here, where we got two magnets with, in one case, the North Poles neighboring one another. So this is a case of magnetic repulsion. That's the forces that are going on. And the second case will be when we got a North Pole and a South Pole facing one another. That's the case of magnetic attraction. That's the magnetic force here. So let's look at the iron filings in this little picture. The field is emerging from this north pole upstairs here, and it's emerging from this north pole downstairs here. So the field lines are coming out, and look what it looks like here. Not only is there a repulsion of the two magnets, but it's as if the field lines from the bottom north pole are literally being repelled from the field lines of the top north pole, and vice versa. The field lines that emerge from the top north pole are being repelled by the field lines from the bottom north pole. So not only are the magnets repelled, but the distribution of field that's created by the pair of magnets, that's changed. The field lines themselves of each magnet are repelled from the other. That's the pattern there. Compare that with the other case. This is a picture of a North Pole and a South Pole end of the magnets nearby one another. So this is the magnetic attraction case, where the magnets are physically attracted to one another. But if you look in this case, this is a case where the field lines are emerging from the North Pole. They would be returning to a south pole of the magnet. Here the field lines from this north pole downstairs here are literally they're not being pushed away, they're being attracted to the opposite pole upstairs here. So these field lines bend upwards to the south pole rather than away from the north pole in the previous slide. So not only can you illustrate the field of a single magnet with iron filings in castor oil, but you can illuminate any magnetic field. This was arrangements of pairs of magnets with your iron filings in castor oil. So you can just map it out. Okay. Want to move on to magnetic field equation. So magnetic field equation is going to tell us exactly how magnetic fields carry magnetic forces. It's like the electric field equation tells you exactly how electric fields convey electric forces. More generally, a field equation, we talked about electric field equation. We're about to talk about magnetic field equation. There's also a gravitational field equation. All those field equations, they all tell you how some property of nature, some characteristic feature of nature, in the electrical case it's charge, how that property of nature experiences a corresponding force, an associated force. So in electrical case, it would be the electrical force. Through a medium or a material or what we call a field that transmits, conveys that force. So every field equation that you meet, every field equation in physics is about saying how this property of nature, say charge, experiences this force, say electrical force, due to this mediator, this carrier, this medium, the electrical field. We're just going to now do that for the magnetic force. So it's going to tell us what property of nature experiences a magnetic force. We don't even know that yet. We don't know that in detail. What property what property of nature experiences that force, and how does it experience that force when it's bathed in, immersed in a magnetic field that is the transmitter, the carrier of that force. So that's what the field equation is going to tell us. As a helper, I brought to class the electrical field equation because we've already met that, and I can see by all your faces you're very comfortable with that, very happy with the electrical field equation. It's going to help us as we look at the new field equation, which is the magnetic field equation. which is something which is a bit more complicated. We've got to learn to appreciate it. So upstairs here, in this slide, the equation over here is the electrical field equation. And downstairs here, this is our new magnetic field equation. And so we've got to learn to understand this magnetic field equation like we had learned to understand the electrical field equation. Let me make a couple of points about the electrical field equation, and then we'll see how they correspond to the magnetic field equation. For the electrical field equation, it tells us when we immerse a charge, Q, in an electrical field, it tells us the force on the charge. So that's what the equation is telling us. The units of the field we could have read off from the units of force and charge. It's newtons per coulomb. The direction of the force is related to the direction of the field in the field equation. We say it's collinear. That's a fancy word we may or may not know, but it just means that either the force is in the same direction as the field, or it's in the opposite direction to the field. That's all collinear means. It's along the lines of the field, either in the direction or opposite the direction. And remember, if the charge is positive, it's in the direction of the field, the force. If the charge is negative, it's opposite the direction of the field. 180 degrees to the direction of the field. So all this information is of how the electrical force is created by a charge in an electrical field is embedded in the field equation. It's a really beautiful summary of the whole workings of the electrical field and conveying an electrical force. Similar thing downstairs here. Charge in the electrical case was the property of nature that feels, experiences electrical forces. It's moving charge in the magnetic case that is the property of nature, the characteristic of nature that experiences or feels the magnetic force. So by moving charge, I'm going to characterize moving charge by a moving charge's QV, the product of its charge, and the product of its velocity, v. So it's moving charges that experiences magnetic forces. You have to have charge, Q. You have to be in motion, have non-zero v, to experience, to feel the magnetic field and experience the magnetic force. So this is the key property of nature that's equivalent to just straightforward charge, don't care whether it's moving or stationary, that experiences magnetic forces. The magnetic force is given by this field equation here. It's the property of nature, the QV, the moving charge, times the magnetic field, just like this was charge times the electrical field, times a sine of an angle, which is a big difference. There's no sine of an angle upstairs here. So where did this come from? In the electrical case, the charge is a scalar quantity. It has a size or a sign, but charge doesn't have a direction. So the field equation in the electrical case is a scalar times a vector. And so you always get another vector that's either in the same direction or opposite direction as the electrical field. In the magnetic case, well, the moving charge, QV, that's actually a vector, not a scalar. Q is a scalar, but V is a vector. It has a direction. So QV, the property of nature that experiences magnetic forces, has a direction associated with it. And so you've got one, in this particular case, this field equation, you've got one quantity, the property of nature that has a direction, multiplied in another quantity, the field, that also has a direction. The magnetic field has a direction. The sine theta is the sine of the angle between those two directions. So the sine theta is in this equation, the magnetic field equation, not in the electric field equation, because in the electric field field equation, the property of nature that experiences electrical forces is a scalar, it's charge. In the magnetic case, the property of nature that experiences magnetic forces is a vector. It's moving charge. So that's the big difference, and it's that big difference, vector versus scalar, moving charge versus charge, that is the reason why one equation has the sine theta, the other equation doesn't have the sine theta. One equation just has one vector on the right-hand side. That's the electrical field equation. The other equation, the magnetic field equation, has two vectors on the right-hand side, and that's where the sine theta comes from. Anyway, this is the field equation for magnetism. It's the parallel of this field equation for electricity. Here are the units, just so that we know. So just like you could work out the units of the field from the units of force and charge that we know. So force is newtons, charge is coulombs. So field has to be newtons per coulomb for the units to be the same on the left-hand side and right-hand side. You could work out the units of the field, B, the magnetic field B. This is the symbol we give to it. From the units of the force over here on the right, magnetic force has units of newtons, charge is units of coulombs, velocity, the new ingredient, that has units of meters per second. So from that you could calculate the units of magnetic field B. They would be newtons per coulomb per meter times seconds. That's a mouthful, and that mouthful of newtons per coulomb, seconds per meter, is called a Tesla. This T here is the units of magnetic field that we'll use. Its name is a Tesla, just like the car and Elon's car, and that's 1 Tesla is 1 Newton per coulomb times a meter over a second. So these are our magnetic field units. Okay, so that slide's just an introduction to the magnetic field equation, like we had introduced the electrical field equation. We see the ideas behind them of a property experiencing a field and experience of force. That's exactly the same for the two field equations, but they are very different in that one is a scalar times a vector, the other is a vector times a vector, and that makes them appear rather different. One more complicated, one more straightforward than the other. So we want to go on and apply the field equation. So the rest of the class is about applying this field equation. Okay. I want to say some more details about the directions in the field equation, magnetic field equation. There's actually three directions, and this slide is to show you what the three directions are and how the three directions are related. So there's two directions on the right-hand side of the field equation. One direction is the direction of the magnetic field that's conveying the force. The other direction is the direction of the moving charge particle that's experiencing the force. So two directions on the right-hand side of the field equation. And there's one direction on the left-hand side of the field equation, which is the force that's experienced by that moving charge. This slide here illustrates those three directions and the relationships between the three directions. Now, the two ingredients in creating a magnetic force are B and the moving charge, the V. And so those are indicated in red here, that's the velocity, and in green here, that's the magnetic field. Remember, we give it the symbol B for some reason. So these are the two ingredients that lead to a magnetic force, and those could be in any direction, right? We could arrange a magnet where the field is up or down or left or right, towards you or away from you. We could make a magnetic field in any direction we like. We could make a charge move in any direction whatsoever we like. We could make it move up or down or left or right or towards you or away from you or any other direction. So the direction of the magnetic field B and the direction of the velocity V, they're up to us to pick. Once you've picked the direction of the magnetic field and the direction of the velocity of your magnetic field and your moving charge particle, that determines the direction of the magnetic force. The magnetic force is pictured here in blue, and it's pictured in that it's perpendicular to, well, firstly it's perpendicular to the two ingredients. So it's going to be perpendicular to the velocity v, that's in red, and the magnetic field B, that's in green. And so these are right angles here. Here's a right angle showing us the force is perpendicular to V. Here's a right angle showing us the force is perpendicular to B also. One other way of thinking about it is that V and B, once you pick V and B, you've picked a plane in which V and B live. So supposing we picked, I picked V to be left to right across the room. And I picked B to be into the whiteboard, from the back of the room to the front of the room. That's picking a plane in which V and B live. V and B live, in that case, in a horizontal plane. V is horizontal, left to right. B is horizontal, it's from back to front of the class. So those two vectors define a plane. They live in that plane, and the force on the moving charge particle will be perpendicular to that plane. So that's the direction of the force is determined once you picked your V and B. If we changed the plane, we correspondingly change the direction of the force. It will always be perpendicular to the plane in which V and B live. So all that's shown on this picture, that angle theta, last thing I want to say is that angle theta in the magnetic force equals QVB sine theta, that angle theta is the angle between those two vectors V and B that are the ingredients necessary to make a magnetic force. So you see on this slide here, this is theta. This is the number of degrees or the number of radians between those two vectors that create magnetic forces, that are essential for magnetic forces, the velocity vector and the B field vector. F is perpendicular, always 90 degrees to those two directions, but you can pick what theta is, right? You can change the magnetic field direction, change the velocity direction to change the angle between those two vectors. Something really interesting about magnetic fields, moving charge particles, and the resulting magnetic forces is that because the magnetic force depends on the directions of the field and the motion, you can get arrangements where the magnetic field vanishes, for example, for certain directions. You can get arrangements where the magnetic field is maximum for certain directions. Specifically, I mean, supposing you had a particle moving with a certain speed, if you moved it in a certain direction, you might get a maximum magnetic force. If you move that particle with a certain speed in a different direction, you could actually make the magnetic force vanish. So just by changing the direction of the particle from up to left or into the screen, you could change the magnetic force experienced by that particle in a given magnetic field. You could change it from being nothing to maximum. How does that work? It works if you think about that equation being the force is QVB sine theta. Supposing, this is the top bullet up here, supposing theta was 90 degrees. Let's think about theta 90 degrees, a right angle. So V and B 90 degrees to one another. Sine of theta, sine of 90 degrees, was sine of 90 degrees. That's the biggest sine can be. It's 1. That means that sine is theta as big as it can be, so the force QVB sine theta is going to be as big as it can be. And so a right angle configuration between V and B creates the largest force. That's the way to make the largest force. Supposing that V and B were parallel to one another, 0 degrees between them. So here's V, my left arm, here's B, right arm. They're parallel to one another. In that case, theta, that angle between the two, that's 0 degrees now. What's the sine of 0 degrees? The sine of 0 degrees, is 0. So this is a configuration, if V and B are in the same direction, where there's actually no magnetic force whatsoever. So this is an amazing thing about magnetism. We just tipped the velocity from going up with theta equals 90 degrees and got a big maximum magnetic force to horizontal, making theta equals 0, and we got we made magnetic force vanish. It depends on the direction. That's complete. There's no equivalent to that in electricity. This is completely new to magnetism. This is a new world feature of magnetism that's completely absent from the world of electricity. So this is really, really interesting. Now, I said that the magnetic force is perpendicular to the plane of V and B. And that's absolutely true. The magnetic force is perpendicular to the plane of V and B. But here's a problem, right? There's 2 directions that are perpendicular to the plane of V and B. Imagine, again, a velocity vector towards the right, a magnetic field into the whiteboard. That's a horizontal plane. What directions are perpendicular to the horizontal plane? Well, there's one direction straight up through the roof. There's one direction, another direction straight down through the floor. We've got to pick one of those 2. Nature picks one of those 2, and the way that we pick, like nature picks the right one, is with what's called the right-hand rule. So the right-hand rule helps us distinguish which of those 2 directions that are both perpendicular to the plane of V and B is the direction of the magnetic force. So this slide here illustrates the right-hand rule. There's many ways of using your right hand. Firstly, you've got to use your right hand. So it's part of the right-hand rule. Many ways of configuring the fingers and thumbs and digits of your right hand to execute the right-hand rule. I'm going to follow the rule from the textbook, which is depicted in this little figure here. So the first, if you look at the right-hand side of the field equation, the first vector you meet on the right-hand side of the field equation is V. So you're taking a walk down the field equation. First one you meet on the right-hand side is V, the velocity. You're going to point the palm of your right hand in the direction of the velocity. Now, we were talking about a velocity that was going to the right. Let's work with this figure here. The velocity is going towards the left in this figure here. So it's right hand, first of all, palm of hand in direction of velocity vector. You then curl your fingers in the direction of the magnetic field. So in this picture here, the magnetic field is kind of coming out of the screen. That's what they're indicating. So it's coming out towards you. So I'm going to curl my fingers out towards you. So this plane here is the plane of V and B. That I've defined that with the palm of my hand and the fingers of my hand, and my thumb points in one of the 2 directions that are perpendicular to that plane. It's pointing up, which was one of the directions that's perpendicular to the horizontal plane. It's not pointing down. This thumb points in the direction of the magnetic force on a positive charged particle. So this is how you pick the direction for the magnetic force for a positive charged particle. So that's the right-hand rule. I think the next slides we're going to look at, so it's fine if I just say that, right? What we've got to do is try and apply that to different situations. So I think that's going to come up next, maybe. No. Oh, well, it sort of is. So that's the right-hand rule. palm of hand in direction of the velocity vector, fingers curled to the direction of the magnetic field, thumb points in the direction of the magnetic force on a positively charged particle. If it was a negatively charged particle with the same direction for the velocity towards the left, say, same direction of the magnetic field, arrows screen say, the magnetic force would be the opposite direction. It's not up, it's actually down. It's because the negative charge brings with it a negative sign, which flips the direction of a vector. Just like in electrical cases, it flips the direction of the vector. So this right-hand rule is for a positive charge. If you're going to think about a negative charge, you've got to think that this is the direction of the force on the negative charge, the direction of the force, sorry, this direction of the force on positive charge, direction of the force on negative charge is going to be opposite. So that's illustrated in this overhead here. Here's a negative charge particle and a positive charge particle, minus and plus. They're both moving upwards in exactly the same direction. So they're both moving upwards through the roof. The magnetic field in both cases is from left to right. So they're both seeing the same magnetic field. So if you think about just their motion and their field that they're bathed in, motion's the same, the field is the same. The magnetic force on the positive charge is into the screen in this picture. The magnetic force on the negative charge is out of the screen in this picture. The forces, on the other hand, are opposite one another because the charges are opposite one another. One's plus and one's minus. So let's take the velocity vector of the positive charge. It's going up, so I'm going to put the palm of my right hand up. The magnetic field is going over to the right. So I'm going to curl my fingers. My fingers only curl one way, right? So I'm going to curl them over towards the right. My thumb is pointing into the screen. That's the direction of the force on the positive charge. That blue arrow is indicating into the screen. Go down to the negative charge. It's also going up. Velocity is going up. The field is going towards the right. Field's the same direction. My thumb is pointing into the screen, but we remember at last minute that the force on a negative charge is opposite the force on a positive charge. The force on a positive charge is into the screen. The force on the negative charge with the same velocity and the same magnetic field will be out of the screen. So this slide is an illustration that you have to be careful about whether the charge is positive or negative when you apply the right-hand rule. Let's look at a few examples. So on this sketch here, we've got 4 examples, 2 at the top and 2 at the bottom. These 4 examples are 4 examples of right-hand rule. There are 4 examples of figuring out the direction of the magnetic force on a moving charged particle in a magnetic field. All these cases involve a moving charged particle in a magnetic field. One thing to remember is not just the right-hand rule, which is a relationship between the velocity vector, the magnetic field, and the magnetic force, but also remember that the magnetic force is always at right angles to the 2 ingredient vectors, so the velocity vector and the magnetic field vector. So as I work through this problem, I'm going to be thinking about both of those things, that there's a right-hand rule that relates V and B to the direction of the force, but also it must be that the force is perpendicular to V and B. That was the first thing we started with. I'm also going to be cognizant of the fact that positive and negative charges will experience opposite direction magnetic forces if they're moving with the same velocity in the same field. So we've got to remember that too. There's one other point I want to make on this slide. These are field lines in green here. they show you the direction of the field. Down it says here, field lines in green show you the direction of the field. And likewise over here on the bottom right. This is also showing you the direction of the field. If we want to show a field that goes into the screen, there's a convention that we've all agreed on in physics for that. The convention is crosses, these little crosses here, mean the field is going into the screen. So it's just an agreement, like north poles and south poles, like positive and negative charges. If we're all on the same page, we all agree that that's the field into the screen. If we had a field that came out of the screen, we'd show little dots. The little dots would show that the field is coming out of the screen. The way I think about it is, I think about a bow and arrow. I think about the arrow, right? If the arrow's pointing at me out of the page, then I see the little tip of the arrow, a little dot. If the arrow's pointing into the page away from me, I see the feathers of the arrow. That's a cross. And so that's just me, but that's the way I remember it. But crosses mean field in, and dots mean field out on these pictures of fields. So this is starting upstairs here, this is a positive charge that's moving towards the right through a region of magnetic field that's pointing into the screen. So let's do this guy. This is the simplest one, I think. So velocity is towards the right. Palm of my right hand is towards the right. The field is in towards the screen. My fingers are curling in towards the screen. My thumb is pointing up. The force, magnetic force on this charge is up. Notice that up is perpendicular to the motion towards the right and the field into the screen. So it's perpendicular to the motion. I'm just using the right hand rule to pick whether it's up or down, basically. That's that case. What about this case here? This case here, we got a negative charge now. That's one difference. We got motion that's towards the left, and we got a field that's going up. So let's try this one. Right hand rule, always the right hand. Going to point the palm of my hand towards the left. That's the direction of motion. Going to curl my fingers in the direction of the field. That's up. My thumb is pointing now in towards the screen. That would be the direction of the force on a positive charged particle. This is a negative charged particle. The force is out of the screen towards you. So this is coming out of the screen. Note again that out of the screen is perpendicular to the plane of V and B. B and V are in the plane of the screen. One's up and one's left. The force has to be perpendicular to those two. We just use the right-hand rule and the fact that there's a negative charge to pick that it's out, not in. Downstairs here, this is an interesting case. This is a case where I can sit back. I don't even need the right-hand rule. In this case, right, I just spot the fact that if a charge moves parallel to the field, or if a charge moves opposite the direction of the field. So if a charge is moving such that theta is 0 degrees or 180 degrees, that means that sine theta is 0. It means there's no magnetic force. And so this we don't need a right-hand rule here. There's just no magnetic force. What about this one here? Maybe this one looks a little bit more scary, right? The other ones always had right angles conveniently between the V's and the B's. It does look a little bit more scary. We have to maybe be a little bit more careful, but we can use the same rules. So positive charge is going up, and the field is going sort of up and towards the right. So right hand up, going to curl my fingers in the direction of the field, up and towards the right, like that. My thumb can only do that in one my hand can only do that in one orientation. My thumb is pointing in towards the screen. So the force is in towards the screen on this positive particle. Notice that that force again is at right angles to the plane of the field, which is in the plane of the screen here, and the velocity vector, which is also moving in the plane of the screen here. if you like to think about it, I don't know whether I should tell you this or not, but I will. You could think of this field here as being a superposition of two fields. One field that goes towards the right and one field that goes up. Okay, so you could think about it that way. What does the field, so if we think about it that way, it's a field that goes towards the right, that's one part of it, and it's a field that goes up, that's the other part of it. What does the field that goes up do? It doesn't do anything. Yeah, it doesn't do anything because it's in the same direction. So the only bit of the field that's doing anything, in the sense of creating a force, is the field that goes towards the right. We turn this problem into a regular old problem with a field, a velocity vector going up, a field that's going towards the right, and the thumb is pointing in. So maybe that sometimes makes it a little bit easier to think through this problem. I don't know. It depends on how you think, maybe. Okay. In the slides, I think I put on the answers to all of these, but we've talked about all this. Quick question then, quiz question to end up with. So this is just one more practice problem for us on the right-hand rule. This is why I think in the actual published quiz you've got a picture. The electron is heading upwards from the bottom of the screen to the top. The magnetic field is from the left of the screen to the right. What is the direction? What is the direction of the magnetic force on the electron? Okay, let me take a moment to wrap this up so that we're all on the same page. In this case, the electron is heading upwards. So I've got my right hand and I'm pointing the palm of my hand upwards. The magnetic field is towards the right, so I'm curling my fingers towards the right. My thumb is pointing into the screen, which would be the direction of the force on a proton, a positively charged particle, but we spotted that this is an electron, a negatively charged particle, so that force is out of the screen. So the electron is being pushed towards you. Notice that that direction of the magnetic force, the magnetic push, is perpendicular to the motion of the electron, V, it's perpendicular to the magnetic field direction B, is perpendicular to the plane that V and B define, which is the plane of the screen. This class we introduced magnetism, we talked about magnetic attraction, repulsion, magnetic north-south poles, but we quickly moved on to the magnetic field as a conveyor of the magnetic force in analogy with the electrical field, conveyor of electric force, and we talked about the field equation. In the next two classes, we'll get more quantitative with numerical problems on the field equation and on what makes the magnetic fields that are used in the field equation.